I'm Lauren Edgar, and today I'm excited to share some of the updates on the Artemis III geology investigation. Our PI, Brett Denevi, wishes that she could be here in person, but as her deputy, I'm happy to share some of these updates on behalf of the team. All right, so just as a reminder, the Artemis III geology team is part of a much broader Artemis III science team, which includes members of the NASA internal science team, the deployed instrument teams, and future participating scientists that we're really excited to bring on board. And the role of the Artemis III geology team is to participate in defining the lunar science objectives for the Artemis III mission, designing the surface campaign to satisfy those objectives, supporting the real-time mission operations, and then performing the preliminary examination of returned lunar samples and synthesizing initial science results from the mission to share with the community. So today I'm going to focus on the first three of those bullets, what we've done to help define the science objectives, how we're defining surface science campaigns to satisfy those objectives, and then how we're preparing to support real-time mission operations. All right, the next slide, whenever we pull that up, there we go, is a reminder of the science goals and objectives for the Artemis III geology team. So these are derived from community documents like the Decadal Survey, which identified several overarching themes to address solar system history, geologic processes, and volatiles. And so our four goals, the first one is goal A, which is to understand the origin and early evolution of the moon as a model for rocky planet formation. Goal B is to determine the lunar record of inner solar system impact history. Goal C is to determine the environment and the controls, determine how the environment controls regolith properties on airless bodies. And then goal D, volatiles, to reveal the age, origin, and evolution of solar system volatiles. So what we have done, we have a science traceability matrix. This has been shared at LPSC and at League and other meetings. Each of these four goals has three objectives. And what I'll show on the next slide, whenever we can pull up the next slide, is how we are working to implement these objectives. There we are. Okay, so this is a portion of our STM. I know you're only seeing a small bit of it here, but we wanted to talk about the site-agnostic STM and how it provides the foundation for planning for how we'll accomplish each of these objectives. So as an example, for one of the objectives under the goal B is to anchor the early Earth-Moon impact history by determining the age of the SPA basin. And so we've given each of our objectives a priority, which is shown in the next column. This is obviously a high priority objective for us, what the hypothesis is that we're trying to test, and then what the observables would be for determining that. We also have noted the required sample types or investigation locations. So for example, in this one, we would need to get access to the rim and within continuous ejecta deposits from at least 2 or more blocky impact craters. And in order to determine different depth of origin, as well as going to other sites to sample geologic diversity. Then we've given each of those a location ID so that we can actually apply this as a template across a variety of different landing sites. We've then identified in the STM the required sample type and investigation types that we expect. So we're looking for rock and hand samples, boulder chip samples, of significant size and mass that we can bring back to enable all of the analyses that are required here, as well as regolith, rock, and rake samples. Okay, so if you go on to the next slide, when you collect all of our objectives and the required investigation types in our STM, this brings us to how do we want to implement this on the surface. And so across all of the goals, all 4 that we have and the 12 objectives there, we currently estimate that at a representative site, we would need to get to at least 10 science stations and collect 35 to 40 unique sample types. And collectively, that would be about 6 hours of task time at stations. That's just for the collecting of the sample and observations that are made, not including the traverse time between locations. And that is what is required to fully satisfy our STM. And the reason why I want to do this is to provide the community with the samples and investigations that are needed to answer these high priority science questions. But ultimately, how much time we'll have depends on, and how much will be accomplished depends on EVA constraints, the time allocated to geology, and the accessibility of targets of interest in the final landing site. All right, if we go on to the next slide. There we are. This is a look at the site-specific planning process. So I've now shown what we did site agnostic. Now when you know the landing site, we start with the STM. The first step is geologic mapping, and so we're doing that at a detailed scale, 1 to 5,000 scale, which is informed by regional geologic context. So the image shown here is just the regional geologic map around the Artemis exploration zone. We then take that and look for some of the points of interest that will ultimately become stations. And so here we're identifying points of interest that might anchor the directions of different EVAs. So if you know you need to get to, more than 2 rocky craters of, a large enough size, if you know you need to get to more than 2, if you need to get to 2 cold regions, permanently shadowed regions, these are things that are going to drive the directions of the EVAs. Then once we know what we actually have access to, then we can fill in some of the less geographically constrained points of interest and associated crew actions. And then ultimately these become our final EVA traverse plans with a lot of iteration with a lot of the flight control team. And then those EVA plans get incorporated into the operations products. So, the CUF checklist, map book, procedures, things like that. Go on to the next slide. All right, so we've had the chance to practice this. Sarah Noble touched on this, but we had our first large surface EVA simulation this past November. It was really exciting to bring together the science team along with the flight directors and flight controllers to carry out science-focused EVAs. And it was a good chance for us to test our EVA planning process as well as how we're going to support real-time operations that will be required for lunar surface exploration. Matthew Miller had a great summary of this at the LSSW this spring that I'd encourage you to check out, as well as there's a published NASA article on this, because this is the first time that we were also using virtual reality to prepare for lunar exploration with the full science team, and so this was a great test of our procedures. If you go on to the next slide. All right, yes, so we were able to test the planning process using actual lunar data at a notional landing site. For this sim in November, it was a site within the Nobile Rim 1 candidate landing region. We were able to follow that process that I identified, using the prioritized science objectives and sample types from our STM, figuring out the points of interest, and then associated crew actions, working with some of the flight control team, specifically the science and task officers, to help develop more EVAs. And for this one, we had 9 different science stations. From this, we've identified a lot of findings and recommendations that we're now being able to learn from and implement for our next big sim coming up this fall. So some of the topics that we're trying to figure out is communication across the team, timeline of the planning process, the planning software, sample plans and tracking tools, the geologic mapping, training, and a variety of other topics. If you go on to the next slide. All right, Sarah showed some scenes from this as well, but wanted to give you a sense of what it looked like for the test of real-time operations. So we had 2 simulated crew members. In this case, the test subjects were other members of the flight control team. The view that they had in the virtual reality setup, which was also the video feed that the SIR, the science evaluation room, was seeing. You can see most of the science team gathered there in the SIR. And for the November sim, we were using a room at JSC as a proxy. But if you go on to the next slide. Sarah showed this, but we're very excited. When you see it in multiple presentations, that it's a very exciting moment for the team because there is now a brand new science evaluation room, which is one of multiple Artemis operations rooms. And so we're excited to get to test this out with our team for the first time. What you're seeing in there, the team is gathered around this large digital map table in the middle front of the room, as well as some of the displays that we'll have at the front. What you're not seeing are a lot of the other science stations and consoles that make up the rest of this room, as well as additional operations rooms at JSC. If you go on to the next slide. I can work. Is there a direction I should be pointing it? Thank you. All right, the other way that we're preparing for operations is through field tests and exercises. We've learned a lot from the joint EVA and human surface mobility test team, the JET test, JET 3 and JET 5. We've also had some of our own field exercises. The images on the right there from a field exercise that we had in the El Paso area earlier this year, practicing what it's like to do the orbital remote sensing and geologic mapping, having simulated crew and how you're building on the geology with each new level, as well as then finally getting to go into the field ourselves and see how much more we're learning. It was a good chance to test out some of the government reference design Artemis tools that you see there in the foreground and work through how we're planning to do some of the observations and geology investigation. I'm not sure that this is advancing, but if you could advance to the next slide. Thank you. The last topic I wanted to touch on was the science evaluation of landing sites that our team has been participating in. If you go on to the next slide. So our team was tasked with evaluating the science potential of landing sites for meeting our defined goals and objectives across a lot of different landing sites. And so how do we do this, rapidly and efficiently for just a quick glance of do these meet our science objectives or not before being able to do the detailed characterization that I showed on the previous slides. So to rapidly evaluate a lot of different sites, we developed figures of merit to evaluate the exploration areas and compared those to qualitative geologic assessment. So for each of the STM goals, you're looking at what are some of the desired targets that are required. So, access to rocks from known impact craters, access to a diversity of environments, access to cold regions and PSRs, and what is the distance, required to traverse to get to those, and keeping in mind some of the slope considerations. So, as I'm sure you know, the actual specific landing site will impact how well the Artemis 3 goals can be addressed. And what the team found is that 30% of the sites that were evaluated looked pretty promising for being able to satisfy our science objectives, but about 40% of them were distinctly, less favorable for doing that. So the example down here in the lower right shows how these are ranked as kind of green for being able to meet our objectives, yellow for you might be able to meet our objectives, but you're going to spend a lot of EVA time traversing to them, and red for this is not a recommended site to help meet our science objectives. So Caleb Tassett, who's here in the room, gave a great presentation of this at LPSC, so I'd encourage you to talk to Caleb and also look at that presentation for more detail. But this was then passed along to the Artemis Site Selection Integration Team for further evaluation. All right, next slide. So yeah, just wanted to share what's next for the team. We are planning for another EVA mini simulation coming up this fall, where we expect to do continued refinement of our surface operations roles across multiple shifts. This is, again, getting a lot of reps and practice in doing this. We're also looking forward to more integration with the Artemis 3 deployed instrument teams, as well as publication and dissemination of initial science planning results. So the broader Artemis 3 science team is working towards a special publication later this year, so stay tuned for more information. And the last slide, if we could advance one more. One more slide. Oh, there was one before that. Yep, the last one's just a summary. There we are. So just wanted to highlight that we've been making some great progress towards the Artemis 3 mission, but a reminder that our motivating goal throughout this work is to maximize the science of the mission and to collect a sample set that will serve the community for decades to come. So we really continue to value community input on these plans. Would welcome you to reach out. A number of our team members are here in person. I know others are online. Feel free to contact us in any way because we'd love to hear from you. And then lastly, just wanted to say, we're really looking forward to the participating scientists joining the team as well, and to eventually executing this exciting and impactful mission. So thank you.